Now I'm going to give you probably the stupidest definition of the course, or at least one of them. So a set of vectors is dependent if and only if it is not independent. Okay, bet you didn't see that coming, right? All right. Well, unfortunately, the notion of independence is kind of easier to understand through the notion of dependence, and then saying, okay, not that is the thing we're interested in. So let's explore the idea of dependence by itself. Okay, so we're looking at the negation of the definition of independence. So suppose that A1, V1 up through AK, VK are added together and give you 0 with not all of the AIs equal to 0. Okay, so for the sake of argument or concreteness, say it's the first one. That's non-zero. It doesn't matter which. So if A1 is not equal to 0, then we can rewrite this equation as, we'll pull the A1 over to one side, and then we'll have all the other terms. So A2V2, A3V3, blah, 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 all the way up to the top, still over on the other side. Yeah. And so since A1 is not equal to 0, I can divide by it. So then I would have V1 is equal to minus A2 over A1 V2 plus up through minus AK over A1 times VK. So what we have here is we have solved VK V1 in terms of the other VKs or VJs. So we've expressed it in terms of the other ones as a linear combination, and realize that what that means in terms of our recent jargon is that V1 is an element of the span. Oh, I just ran out of room. V1 is an element of the span of V2 through VK. Okay, so this expression right here then is what we would call a dependency relation. It shows that V1 depends on the other VIs. So that's a dependency relation. All right. So so a set is independent if and only if no element can be written as a linear combination of the others. All right, so this means that if V1, for example, were an element of the span of the other guys, then what happens is if we look at all the stuff that we can build out of V2 through VK, well, we can build V1. So by adding V1 to the set, we get nothing new. So the span of V1, V2 up to VK is exactly the same as the span of V2 through VK. So this means that V1 is redundant. It's useless. We didn't need it. We could build anything we needed to just with the other elements of the set. So an independent set contains no redundant information. So this means that say if V is our name for the span of S, and S is independent, then since it's independent, no strict subset of S can span V. Okay, so by strict here, I mean strictly smaller. So it has a strictly fewer number of strictly smaller number of elements. Sometimes this is also called a proper subset. Okay, so this is the meaning of independence. It means that no element can be built as a linear combination of the others, and it also means that the span of whatever you have cannot be manufactured from as the span of any strictly smaller subset. The other way of thinking about linear independence is in terms of uniqueness of solutions. So here's an example that explains what I mean. Suppose we take S to be the set of, we'll take V1 to be 2, 2, V2 to be 1, 2, and V3 to be -1, 0. Okay, now this set is a dependent set. And my justification for saying that is that V1 can be written as V2 minus V3. Okay, so we can ask the question, like say we were in the previous unit and somebody asked you the question, is 4, -2 in the span of S? If so, find its coordinates. So by coordinates here, I just mean find the coefficients that show it as a linear combination of elements of S. All right, well, let's see. So 4 minus 2 can be written as 5 times 2, 2 minus 6 times 1, 2. However, we can also we can express this vector here, V1, in terms of V2 and V3, like we have over here. And so we can rewrite this as 5 times, and then here we've got 1, 2 minus -1, 0. And then we still have the other term over here. And so then collecting up the coefficients, I have a coefficient of -1 times 1, 2 minus 5 times -1, 0. And so I have, here's one perfectly valid way of expressing 4, -2 in terms of elements of S. Here's another perfectly valid way of expressing 4, -2 in terms of elements of S. And they have different coordinates. So I mean, the coefficients here and the coefficients here are very different. So what I'm talking about is we have uniqueness of solutions.